Hi, this is the last video in a series that presents some new ideas about the universe that I call black marble theory. We've introduced a lot of new concepts in this theory, some of which provide alternatives to the propositions of current cosmological science. So let's review the major points. We've suggested that there's a state of matter that hasn't been discovered yet that I call black matter. Unlike ordinary matter, it's not made of particles, and it doesn't contain any space at all. It's the densest stuff that can exist in the universe. We've suggested that at the center of a black hole, there's a minute sphere of black matter that I call a black marble. And I suggest that there's a black marble, not a singularity, at the center of every black hole. We further proposed an alternative to the creation of our universe. The current theory proposes that the new universe appeared from nothing as a singularity, which then underwent an immense expansion called inflation in the first second of time. Instead, we suggest that the Big Bang was the result of an explosion of an extremely large black marble that became unstable and began converting its matter to energy via the E=mc² reaction. This explosion created the space and provided the energy for its initial expansion and left the residue of ordinary and dark matter in the structure that we observe today. We propose that the mysterious stuff we call dark matter is comprised of the black dust made of tiny smithereens of black matter that is the residue of the Big Bang explosion. Now, another major question addressed by this theory concerns the recent discovery that the rate of expansion of our universe is increasing, and we need to find a source for the new energy that will cause this to happen. Scientists have given the name dark energy to this force. And the most prevalent current theory is that it's an inherent property of space itself. Most cosmologists expect it to grow exponentially as the space in our universe expands at an ever-increasing rate until the universe destroys itself in an event they call the Big Rip. On the other hand, black marble theory takes the view that the energy needed to accelerate the expansion rate comes from the conversion of ordinary matter to energy in stars and supernovas. And we call this bright energy. And we predict that when the supply of ordinary matter is depleted, acceleration will stop and the universe will just slowly dissipate into the void that it came from. Now, because so many ideas in black marble theory are new, it's only reasonable to expect that they'll be justifiably met with a great deal of skepticism. In its favor, the theory predicts that the universe will look exactly the way it does as we see it, and provides simple and logical and plausible answers to many, perhaps most, of the major questions confronting cosmology today. However, in order for black marble theory to be accepted as a reasonable explanation of the universe, it must pass extremely challenging tests. First, it must not contradict any known and well-established facts that we've directly observed in our extensive study of the universe. Secondly, it must produce predictions which may be tested and can falsify the theory if they're found to be wrong. In other words, there's a great deal of work that has to be done before black marble theory can be accepted as a valid addition to present cosmological thought. Now, the current accepted theory called the lambda CDM model explains everything that we've been able to observe with very precise accuracy that gives us a great confidence in its truth. Now, the period of actual observation that it's based on began from the time the universe emerged from the primordial soup at the moment when the atoms were formed and the photons were first released into the universe and it became transparent. It's critical for black marble theory that it not contradict these observations, although it may account for them in different ways. We've described how the current theory is based on the idea of inflation, and how black marble theory proposes to replace it with the alternative of the explosion of a black marble. Well, a lot of work needs to be done to give it credence. Now, since direct observation is impossible, this work will have to be done by computer simulation. And to be plausible, the model must start with the explosion and then interface smoothly with the lambda CDM benchmark model at the beginning of the observational period and bring it up to the present era when the acceleration of universe expansion was discovered. Now, in dealing with the acceleration, lambda CDM and black marble theory have completely different explanations. Lambda CDM proposes that the idea that dark energy is an inherent property of space, while black marble theory explains that it comes from converting ordinary matter to energy in stars and supernova. Now, the challenge for black marble theory is to show that the bright energy that comes from the conversion process will be equivalent to the dark energy density that is calculated for the lambda factor. Well, such a conclusion will require a great deal more data regarding the history of the expansion of our universe. And fortunately, we live at a moment when such data is just about to become available. Several new observational techniques are currently being constructed and deployed. The first of them, called the Dark Energy Spectroscopic Instrument, or DESI, is being tested at Kitt Peak as we speak. It will provide a survey of 35 million galaxies that will provide a history of the universe expansion and energy density going back 11 billion years. The results of these new observations may provide observational evidence toward the support or the falsification of black marble theory. A promising prediction that we may be able to investigate in the near future concerns the precise value of the Hubble constant, or the scaling factor, as it changes from the early universe up to now. In the lambda CDM approach, dark energy is proportional to the expansion rate of the universe, which begins at the birth of the universe and increases in a continuous, smooth, exponential curve as the universe approaches its end. Now, the bright energy curve is proportional to the population of stars and supernova. Star formation was very active in the dense early universe, and it peaked about 3 billion years after the Big Bang. But then, as hydrogen clouds became more dissipated and rare, fewer stars were born. And the rate today is only 1/30th of what it was at the peak. Now, as the older stars die out, the energy density from bright energy will decrease, and the Hubble constant will decrease with it. So the shape of the curves predicted by dark energy and bright energy will therefore be quite different. The values for the bright energy curve should be higher than those predicted by lambda CDM in the period from 3 to about 6 billion years after the Big Bang. And then in our present era, they should begin to trend lower and separate from lambda CDM in the near future. These predictions need further study to refine them, and we may be lucky enough for a discernible difference to be observable today. So as our observations become more accurate, we may be able to determine which theory better describes our universe. Now, if you have background in formal cosmology, you'll recognize that I've avoided discussing the equations that lead to a precise description of the behavior of our universe, including general relativity and the FLRW metric that described the expansion. Well, these equations provide the mathematical foundation for black marble theory. And luckily, Einstein and others have already done the work, and they provide a very solid foundation for the propositions of the theory. And I hope you'll forgive the simplifications and find that they present an accurate explanation of the basic ideas of current cosmology. And I also hope you'll find the proposals of black marble theory are intriguing enough to merit further attention. They're simple and logical, and they provide ready explanations for the unanswered questions of the current theory. But they also need the formal study that will either falsify them or find them worthy to be added to the amazing science of cosmology that explains our universe. I hope the ideas presented here will help point the way.